Okay, everyone. So welcome to the first ArduPilot log analysis seminar. So many thanks to Jem for suggesting this. So this was on the Discuss server, and he popped up a post suggesting that we have a seminar to teach people a little bit about log analysis. It's deliberately quite informal, this, so feel free, anyone, to shout out and tell me what I'm doing wrong or point out other features in the log. We've allocated 2 hours for 3 logs. I do a lot of log analysis. I just had a look here now. I've got this folder where I keep all the logs that people send me for analysis, and I did a quick count, and of the bin logs, not counting the dot log and not counting the t log, I have 3,601 logs that I've been sent over the years to analyze. But a lot of those are private, so it is great when people post a log for analysis if they can post it publicly, because that allows me to then do a public reply on the analysis and to put up a document and things. So I've picked 3 logs, not quite at random. And if you have a look in the chat there, you will see the link to a little document which has links to where you can download these 3 logs so you can follow along. And also the comments. So I'll just start sharing my screen and go through the comments so people can see my screen there now.
George, yeah. It looks like you haven't got global permissions for those logs.
I don't have that. Okay, so let me go and fix that. So I should have had global permissions for the whole folder. So
you're going to get a lot of requests in your email.
Yeah, let me just go and make sure that everyone anyone on the internet can view. Yes, I've done that, but let me go and stick it on the individual folders. Anyone that on the internet can view. Let me maybe I just gave the wrong link.
I was able to download it. I downloaded them as a zip file. I mean, I just clicked on download.
Me too, yeah.
Yeah, I suspect people have just got, maybe the link I put in the chat isn't the public sharing link. So try that link.
I think that's
the issue.
Just double click. Just double click the right
so I gave people the wrong one. I think I put the right link in the Discuss one. So yes, people should have the link there now. Okay, great. Yep, all good. So the first log that I chose was the one that Dale 2020 popped on the Discuss thread. And so the request he put in, he had a Valentix Ranger EX. So that's, for those who don't know it, that's a fixed wing, sort of 1.8 meter, maybe, something like that, wingspan, 4-channel, actually 5-channel fixed wing, because it's got flaps. And this was his comment. So I'm preparing a log plus FPV video from beta 4, that's plane 4.1.0 beta 4 from the Valentix Ranger EX. Rolling auto takeoff, auto tune, which corrects a bad oscillation, successful cruise mode, successful auto landing, but 10 to 20 meters to the right of the target landing point. Landing too far to the right. I'd really like to understand how to use the logs to improve ground steering. Now that one is often quite difficult, and I may well hand over to Paul to have a look at that. You'll see it's not ideal. Ensuring my flight PIDs are good and diagnose my poor horizontal landing accuracy. All right, so let's bring up Dale's log and have a look. And I'll just show you the process that I go through when I open up someone's log. And we'll just pop this away. I will probably be doing stuff, actually filling in things here. So it's quite a large log. It's taking quite a long time to load. Sometimes I split up the log by flight mode to make it a bit faster to analyze. So let's bring up the map. And the first thing I tend to do is bring up the map here. And just to get an idea, first of all, it's fun looking at where people are flying. Looks like a lovely flat fields, must have a friend who's a farmer. And so a lovely area. And so it's in the Northern Hemisphere somewhere. All right. So what I often bring up next is just to see the sequence of the flight modes, to see what he's up to. and we see he's sitting on the ground with no movement there in fly-by-wire array. Then he's got a flight in auto mode. Then he does a bit of cruise mode. Then he does an auto tune. Then back to cruise mode. Then into auto mode again. Then back fly-by-wire array. Looks like he's landed and took off again. There's a great big gap here. So the second flight, and then auto and auto landing at the end here. All good. Now, I often look next at the messages that we get with the messages command. So this is Mav Explorer. Mav Explorer works on Windows, Mac, and Linux. As I mentioned earlier, there are several different good log analysis tools for ArduPilot. This particular one is the one that Peter Barker and myself maintain, which is Mav Explorer. And it's one that is great if you don't mind a little bit of command line. For example, I just type the command messages to get all the messages from the flight like that. There's also plot.ardupilot.org, which is very good. So this is that same log loaded with plot.ardupilot.org. And that has a nice 3D viewer here. So you can view the flight path in 3D and, you know, a nice system for sort of zooming in on parts of the log up like that. So very nice log analysis tool that's online. And there's also the one built into Mission Planner, which is very capable, particularly good at the scaling of the Z-axis and selection of elements to plot, but just one graph at a time. And there's also the one that's in APM Planner, and I think they're the main ones at the moment. All right, so once we've got a basic idea of sort of, you know, understanding what they're doing, we can see that he's flying FMU V3, which probably means a Pixhawk 1. And he really probably should be using the Pixhawk 1 firmware rather than FMU V3. It's a common thing that people find they use these FMU rather than the specific board firmwares, but harmless in this case. He's flying Beta 4, and we can see he's using S-Bus. He's got a U-Blocks that's been detected, and he's doing an automatic takeoff here. You can see these are the messages from when he's doing the auto tune, a few messages from when he's flying the mission, and he's using a rangefinder. You can see where they're seeing the rangefinder engaged during the landing, and that's about it. They're the main messages. Next thing I tend to look at is what sensors they've got. We can see he's got a single MS5611. So got this dev ID command that shows all of the device IDs that are registered. And so we can see he's got an MS5611. He's got 2 compasses that he's found here, a external HMC on I2C and the LSM 303D from the Pixhawk 1, the internal one. And then we can see he's got 2 IMUs, the MPU 6000 and the LSM, which is the classic sensors from a Pixhawk 1. Okay, so let's have a look at, I tend to jump into the state estimation next and just see whether the state estimation is okay. And so I'll bring up the innovations. I'll also just double check that he's using the EKF. So you can use the param command to look at the parameters that he was using. You see he was setting the EKF type to 3 and EK3 was enabled. All right, so he's using EKF3, and we can bring up the innovations. Now the innovations are a good first measure of how things are doing. And I'll just bring up the second lane innovations and seeing if they're different. So what these scaled innovations are, these are the scaled innovations, and what they tell you is how close the EKF is to rejecting a sensor. So these are the innovations, and these rather cryptic, axes here. V is velocity, P is position, H is height, M is the magnetometer, and VT is true airspeed. And what it's showing is that all of his, at one point, his velocity sensor, which is likely to be his GPS, is going above 1 and is being briefly rejected. And his other sensors are all below 1, so they're not being rejected, but they're not really low. The main one that's above, that's significant at the early part is his VT true airspeed. Now, that's not uncommon to have a noisy airspeed sensor. We see that the 2 lanes are fairly similar. So he's not getting a much difference between his 2 IMUs. We could also look, so these are what's called the scaled innovations. Yeah, Paul, if you want to jump in.
And yeah, I'm just saying that the way the scaling works is if it's greater than 1, it means the EKF has rejected the measurement because it's inconsistent with its own estimates by too large an amount, and should be below 0.5 for normal up and around flying. And on the emission planner screen, when you see if it goes over 0.5, from 0.5 to 0.8, that gives you an amber warning on the emission planner. And when it goes over 0.8, it starts showing up as red for the EKF health status. So that's how you correlate those graphs to what you see on the little bars for the EKF status on mission planner.
Thanks, Paul.
And if we have a look at that log, because it's just the velocities where you're seeing the larger innovations, what I do typically next is have a look at the GPS receiver's reported velocity accuracy to see what's happening. And on this flight, that's a very interesting plot.
All right, so let's have a look. So as Paul said, these scaled innovations tell you how close you are to rejecting. And we see it at here, it's actually rejecting the velocity a little bit. I tend to bring up the SI unit innovations next. So these are the innovations, in this particular case, in the northeast direction. So this is the horizontal innovations, and these are in meters. So what that's meters per second, velocity is in meters per second. So what's that telling us is that the EKF's internal estimate of the velocity of the vehicle and the GPS's estimate of the velocity of the vehicle differ by about 3 meters per second here while it's in up and away flight. Now let's just see what it was doing at this time when it was starting to reject. If we zoom in on that part, what happens with Nav Explorer? This is one of the cute features in Nav Explorer is as you scroll the graph here, you'll see the little snake of the path scrolling here. So as we see here, we see he's coming down this flight path here. I've got to show off this feature. He's going on a nice straight path, and then he comes into a turn. So when he turns here, you'll notice we start getting some significant velocity innovations as he comes through that turn. Okay, and then it settles in, and now it's okay again. The velocity innovations are dropping in those straight flight. So basically, we're getting higher innovations during a turn. All right, so as Paul suggests, let's go and have a look at the GPS accuracy. Now, notice we haven't even got to the actual questions that Dale asked about his log. And I usually start with the state estimation first, because if you dive straight into the part that the user is focused on and don't check that the state estimation is okay, you can miss a major problem. Because it's very common that state estimation is the root cause of issues. So it's really worth looking at the state estimation early on. So what we see here is he's sitting around sort of 15, 16, 17 satellites, which is fine. If we see what sort of GPS it is, we can see that it was a, and if we have a look at the message, so that's an 08, this is an M8, right? So this is an M8 GPS, so that's a reasonable number of satellites. But what we see here is the speed accuracy is sitting around, mostly around sort of 0.3, 0.4, 0.5. Speed accuracy gets worse here, but in particular, the VAC, which is vertical accuracy. It's a bit misleading. You think it might be velocity accuracy, but that's actually vertical accuracy is rising up. And then horizontal accuracy is also rising up. So basically, the GPS is getting less confident in its estimates when we're in a turn here, and they start getting more, it starts getting more confident as it comes down here. But these are not great numbers. I should also mention that u-blox M8 is notoriously optimistic. So when it says, 3 meters vertical accuracy, it could be off by a lot more than that. And the same with the speed accuracy. Paul?
I'm just pointing out that it's common with GPS manufacturers to specify what they call a circular error or an error probability, which means the number means that 50% of the time it will be within that. 50% of the time it's greater than that, but greater than that is a very big space. So.
Indeed. And if you want to see more about SEPs and accuracies, then this blog post should give you a very good idea. This is a blog post I did some months ago. I'll just see if I can make this thing now show I can't make it show the link. Damn it. The little chat window won't pop up. There it goes, finally. All right, chat. And so that one there, that has a lot more information about circular SEPs and the sort of SEPs you expect from a GPS, at least when it's sitting on my table here, not flying. All right, so we can see here that this GPS, it's not great. It's not terrible.
Well, no, but actually it is terrible.
Oh, yeah?
In the turn. You know why? Because there's the one bit of the accuracy, which is the first indicator if you're getting interference on the GPS or a degraded signal, and that's the speed accuracy, which is the Doppler shift. And if you have a look at the Doppler values, where they really start that Doppler accuracy drops, you can see that corresponds to where you see the large innovations on the EKF.
Right. So the EKF, the GPS is saying it's really quite uncertain about this velocity. And the EKF is saying that velocity isn't consistent with my other sensors. And so at the points here where it goes above 1, the EKF is actually rejecting that velocity and saying, nope, I'm not going to fuse that. I reckon I have a better idea using the IMU and the other sensors than what you have. And for those little moments, only short periods of time, the EKF doesn't use that velocity reading. All right. Okay, so that gives us an idea. And for a hobby grade plane, it's not uncommon to get this sort of thing. It's definitely worse than it should be on this velocity. But this is just something we sort of note in the background and see whether it has an impact on the actual questions that he's had. So we can have a look at a couple of other things. We can have a look at how he's doing on attitude control. Now, before I look at the attitude control, I tend to look at the consistency of the roll and pitch attitude estimates. All right, so this is, we've got our different attitude estimates. We're running 2 EKFs because we've got 2 IMUs and it runs what's called 2 EKF lanes. And we can see that the 2 estimates of roll pretty much align. There's a small difference here, right? In a sharp turn, we can see a difference of like 2 or 3 degrees here. It's not huge, and that's not really uncommon. A little bit of difference here, again, a degree or 2, so not really uncommon at all, particularly as they're not the best IMUs. The Pixhawk 1 was fine in its day, but is a little bit dated on IMU quality now. Let's have a look at the pitch and see whether they're nice and consistent. So here's our pitch estimate, and you can see again the 2 different pitch estimates. This is the overall one that it's using, and these are the one from the 2 lanes separately, and we can see that they're pretty consistent. We don't have any problems. So the reason I look at that first, rather than going straight to the attitude control, is if the 2 lanes are inconsistent in their roll and pitch estimate, then looking at the attitude control may not mean much, because it may not actually have an accurate attitude that it's actually tracking. And we can also check the yaw and see how it's going. And we can see that the yaw estimates between the 2 are quite consistent. All right, a little bit of inconsistency here at that point. I think that's when it's sitting on the ground, so not uncommon.
And we can also check the yaw from the, if we're worried about maybe the compass is pulling the yaw off, then you can look at the yaw from the Gauss, particularly for planes, from the Gaussian sum filter.
Indeed, yeah.
We introduced, which is something that doesn't rely at all on compass. So it's like an independent check.
Yes, so we can, that's what Paul's talking about there, is this GSF yaws element, which I'll just bring up. And okay, my machine's starting to get a little bit overloaded. So what this is showing us is lots of yaw estimates and seeing if they've converged. So what we see is several different yaw estimates, which at this stage of the flight, they then converge on the one estimate here, but then he reboots and goes again. Or if we, so this is a yaw estimate that is based on the IMU and the GPS, correlation between the IMU and the GPS. And it's a great way of double checking whether the yaw is correct. You can see it converged here fine. So it's actually a multi-postulate filter, I think it's called, Paul.
Yeah,
is that right?
Multiple hypothesis. It
multiple
starts out
hypothesis
assuming
filter.
you know nothing about your yaw.
Yep.
And so you start out.
So we have all of these different yaw estimates. So
Yeah.
it's a bit like the guy with 2 watches never knows the time. Well,
This
when
is the guy
both
with
watches
5
show the
watches.
same time. Yeah, a guy with 5 watches, and when all the watches show the same time, then we're pretty sure we know what the time is. All right, so I think we've had a look enough at state estimation. The state estimation is good enough that we can start having a look at the other things. So let's have a look at how his attitude control was going. All right, so if we have a look at overall attitude control and we zoom in, he did a little bit of an auto tune in this flight using the new auto tune code. And the distinctive signature is where he's doing these rapid rolls either way, and then some rapid pitch movements like this. So there's the rapid pitch movements. And we can have a look and see whether his auto tune converged okay. So what I'm going to do is just concentrate here on the auto tune that he did by selecting the flight mode here, by choosing just the one flight mode. All right. Then what I'm going to do is have a look at how it converged from the feed forward. So if we go here, we can see this is, so the way the tuning works with the new tuning controller is, if I show this, we can see that it's got a feed forward and it's got a P and it's got an I and a D and it's got various filter terms and a time constant. And this is the estimator for the feed forward. And it has these green points, FF0 are the point estimates, where it's getting like a single sample for each time he does a little turn. If we have a look at his what he's doing in this part, and we can see that here he's doing these rapid rolls, and each time he does that, it gets a sample of the feed forward. Then the red line is a 4-point median filter, and you can see that that settles into a feed forward value quite reasonably. So we're all happy with that. Then we can look and see what it did in the P and D elements. So this is the ATRP message. ATRP 0 is for roll, ATRP 1 is for pitch. So ATRP is auto tune roll pitch. So we're limited to 4 characters in our log messages, so sometimes they get a bit cryptic. And what we can see happened is that it started off deliberately bringing his P and D gains nice and low before it started the tune, and then it raised the D term up until it saw oscillation. And we can actually see the oscillation if we look at what's called the roll D mod. So this is the roll slew rate on the right-hand axis here, and we can see that it's getting up to peaks of about 300 degrees per second. And the D mod, which is the Paul's neat little oscillation detector, where what that does is that detects when you're oscillating and automatically backs off the gains, right? So we can see at this little point here that the oscillation detector detected that it's oscillating and backed off the gains. And that's what the auto tune is using to automatically detect when the maximum possible gain has been reached. So you can see it raises the D gain up and up and up. And then when it detects this oscillation, it goes whack and brings it back down to a non-oscillating state. And it settles in on that D gain, all right? And then what we see is it doing the P gain. Once it's got the D gain, then it starts raising the P gain here. And as the P gain raises up, eventually we see, we see that it gets oscillation due to the P, and then it goes whack and brings the P gain back down and settles into that P gain. And what we if we have a look at the messages while you're flying that, you get these little roll D messages on the console, then roll P, then roll finished. All right, so that's doing, that is all operating correctly. And I'm having a particular look at that because we've only just redone this auto-tune algorithm. So I wanted to make sure it's behaving okay. And that looks reasonable to me. We'd have to look at the end result of it in a second, but it seems to be behaving the way it was designed to behave. We can have a look in pitch. So very similar. So we can look at the pitch feed forward, and we can see a lot more variation in the feed forward estimates in pitch. And this I'm finding to be quite common. It's not something that I really resolved properly. It's quite common that we get an asymmetry in pitch where, and I don't know whether it's because of the asymmetry in the linkages, but we quite often find that if we look at the attitude control here and we zoom in on this part where he's doing the pitch auto tune, we can see that when he's pitching up, he gets a lower feed forward estimate. When he's pitching down, he gets a higher feed forward. I think if we zoom in on these, it might be clearer. You can see that there's this periodic matching, and it ends up using this median filter, which ends up sort of somewhere in between, but it can mean you get this little bit of oscillation in this one. And it's something that would be nice to address. We may even need some sort of asymmetry because it's quite common that we see this asymmetry in the pitch control. So it ends up with this sort of middling value for the feed forward in here. All right, so next thing we look at is how it did on the auto tune with the P and D gains in the auto tune. And we can see a very similar pattern where it raised the D gain and then dropped it, then raised the P gain, then dropped it. And if we have a look at the oscillation detector, and if we look at the pitch D mod, then we can see that it raised the D, then it got an oscillation, then backed it off, then it raised the P gain, got an oscillation, and backed it off. And this is the same process you would do for a manual tune. It's just doing it automatically. And so this auto tune is designed to mimic the process that somebody manually tuning their aircraft would use. Raise D until it oscillates, back it off, raise P until it oscillates, then back it off. All right, so we can then have a look at how it did. It does back it off a long way, by the way, so sometimes it backs it off a bit more than is really necessary. What we can do now is come out of the auto tune and go back to the overall roll rates and pitch rates we got. And so we'll just look over the whole flight. So after the end of that auto tune here, he then did a little bit of flight, and we can see this cruise mode where he did a couple of turns. And one of the key things people often don't understand is that the attitude controllers in ArduPilot are rate controllers. So the key thing to check is whether it's achieving the desired rate. Achieving the desired attitude won't necessarily happen depending on your time constant, how rapidly you're trying to do the turn. So if we have a look at the attitude control here, which is what people ultimately are wanting to achieve, you see things like the attitude control, the roll here lags the desired, right? And that's because we have roll rate limits. So we've demanded a change in attitude faster than the rate controller has been configured to allow it. But if we have a look here at the actual achieved rates, they're actually very good. So that means it's holding the desired rate very nicely and with a little bit of lag, right? And here again, it's tracking the desired rate pretty well, not quite reaching the peak that we requested there, but not far off. So that's quite an acceptable tune for a foamy type aircraft like this. Foamy aircraft tend to, you know, they're a little bit floppy, and the linkages often are not quite perfect. But that's really a pretty good roll tune, right? We could have a look at the pitch tune and say, so we look at the pitch rates and we'll see, now he didn't do as large pitch movements here, but it's a little bit low. It's not quite achieving what he wanted. Let's see whether he did any more pitch movements later on here. There's this one in, yeah, this is when takeoff and landing, that when you're hitting the ground, then the pitch controller doesn't really have much of a chance. We can see in here though, there's a fair bit more noise we've got here. And so that noise, if we, well, it's really sort of, it's wafting around a little bit. It's actually fairly low frequency. If we zoom in here, so you have a good idea. Yeah, it's actually, it's not really noise. You start thinking about noise when it's sort of, you know, 10, 20, 30 hertz, that sort of thing. You can see that it's more wafting up and down a little bit. So that isn't as tight as you'd like it in terms of the pitch rate control. Now that may be partly a result. Remember we said the feed forward wasn't necessarily great. Also, I suspect that the D term isn't quite as good. Paul?
I think it, yeah. So you can, something that also shows up there, you can see that when you get this disturbance and the measured pitch rate, it pitches up, it's getting a little, hits a bit of a gust, for example, and you can see that the demanded pitch rate is then going down, okay, because the angle control law, which is the one that says, what's my demanded angle, what's my measured angle, I'm going to demand a rate, that's saying, oh, I need to put the nose down. It's demanding a nose down pitch rate, and then the pitch rate then and then swings back the other way, because it often does that with a gust response, and then you can see the angle controller sort of trying to catch up with it. And when I see that type of response, that usually says to me that it's a feed forward is not going to help it very much, because most of it's just the response of the airframe. So if it was a case of the feed forward doesn't help you if it's just the airframe responding to a gust, but what helps you there is gyro feedback or damping, which is essentially the P term.
Right. So we can see here that the actual, if we look at the slew rates we've got on the server is very, very low. We could almost certainly raise the P and D somewhat higher than what the auto tune gave. And now one thing you can also get, he could do, he could raise those terms, but he might also benefit from putting in a filter to get a bit less noise, which would enable him to have a higher gain without risking oscillations. So he's got a gyro filter currently at the default of 20 hertz. He might be able to benefit by putting in a harmonic notch filter and that might allow a higher D term. But the first thing I would try is just start with the gains from the auto tune, but then push up that P and D gain a bit more. And like I would probably start by doubling that D gain. And it's these days, it's not a lot of risk pushing up the D and P a bit higher. You're not going to suddenly massively destabilize, because we have this slew rate max, which detects oscillation. So if you do push them up a bit too high and it starts to oscillate, it will oscillate a little bit, but it's not going to go totally out of control.
Yeah. And there's something else that you can check too if you're worried about pushing up your P and your D. I like to plot the P and the D contributions to the elevator movement which we log.
That's this one here. That's this here.
And if you zoom out, because that's just looking at a very single bit, but if you zoom out and take a bit where it's just flying around, make sure you get the bit in the air and not on the ground, because that can be, and then zoom in to see how much are we getting, how much of that is P and how much is D.
That's right. It's almost all now.
Well,
notice
I usually find it easy just to plot the P and the D together to make it a little bit easy, but you'd have to mentally,
Yeah, if you have a look at the green line here.
Yeah, so if you just plot P and D.
Sure.
And have a look at how much noise there is on P and D, because the big problem with running too much D is that D can heat your servos up, because it takes the engine vibration, the noise gets passed onto your servos, and then the servo motors are constantly trying to catch up with it, and your servos start to go hot.
Yeah, these are very low. So
and if you have a look at that, because the units of that essentially plus or minus 45 is maximum elevator. It's not maximum servo, it's maximum elevator. In fact, it's less than maximum servo. So they're very small amounts. We're not hammering a lot of noise into the servo. And if your servo is not getting hot at the end of the flight and you're seeing low noise levels like that, it's usually quite safe to make those terms higher. Yeah.
You expect these, so you can see the overall contribution to the flight. In fact, the main contribution, if this thing's flying on iGain, which means he's got a significant, he's needing a fair bit of up elevator, right? Which means he's nose heavy, or he's just got the wrong offset. Now we can see whether he's got servo auto trim. Servo auto trim. He does have servo auto trim. Let's have a look at what his trims ended up being. So his servo functions, not param set, just param servo auto functions, and his elevator is channel 2, which is 19. Param servo 2, and in fact what we can do is have a look at param change on servo 2 in the flight, right? You've got this little command param change, which is quite useful to see what parameters changed during the log, and we can see that the servo 2 trim changed a bit during the flight and started moving up, but it would have hit the limit. We only allow a certain range of automatic trimming. And if we look at the overall flight, this little AETR message I'm bringing up I find very useful. So this is the values going into the mixer, right? The mixer is what turns a virtual 4-channel plane, which is aileron, elevator, rudder, throttle, into the actual surface movements, which could be elevons, or they could be flaperons, they could be V-tails, whatever. We've got this notional 4-channel plane that we're flying. And if we have a look at this and we look at, say, the auto flight here, so here it is flying around in auto, right? 4,500 on this graph is full up elevator. You can see the elevator was, more than halfway up for most of the flight. So that means it's really struggling to hold the nose up, right? And that means he's basically nose heavy, and it'll fly better. A plane likes to, it's like balancing on a ball, right? It likes to be, nicely balanced. If it's nose heavy, lots of weight pulling it down, and then you're having the elevator pulling up to compensate, the plane's constantly struggling.
Either that or the linkage needs to be adjusted.
Yes, that's right. Yes.
Because sometimes with servos, it's easy to put something back on, put the servo arm back on, get a different spline, and you can end up with a non-zero with the elevator being in the wrong position with that zero servo. Does this plane fly manually at any time in flight? It doesn't, does it?
I don't think he flies it in manual. Yeah.
Okay,
but it clearly needs a fair bit.
Aware of where the elevator trim is. Yeah.
That's right. Yes. So it's almost certainly just a fair bit nose heavy, right? And that is particularly important for landing at low speed, where you sort of run out of elevator travel when you're really nose heavy.
The reason I caution about immediately jumping to nose heavy, it's possible that it's not nose heavy and that the elevator just hasn't been mechanically adjusted, in which case moving the center of gravity back could cause a bad situation.
Yes. He needs to check. The way I would check it is after you land it, you pop it into manual mode and you see where the surface is, right? And now the surface will be a little bit I would expect it to be a little bit up because the servo auto trim has been trying its best to compensate, right? But if in fact it's down, right, when he lands and pops it into manual with no stick inputs, then that means indeed something wrong with the linkage, right, or the servo, or on the wrong spot on the cog or whatever, on the gears. So he'd have to look at it himself and check, and also check. I mean, the Volantex EX has little markers for the center of gravity under the wing. So he can also, you know, when you're not out in the wind, you come indoors and you balance it on your fingertips and see if it's balancing at the right point. Although you've got to be careful, some manufacturers get those center of gravity points wrong. You know, if indeed the elevator is up and it's still doing, you know, needing even more up elevator in flight, then it really is, your center of gravity is off, or something else. I mean, you can even on planes like that, the tailplane is like screwed in or glued in. If that was glued or screwed in at the wrong angle, so your tailplane is actually at the wrong angle of incidence, then that would also do it, right? Or even your main wing, you know, not screwed in right. So you need to do a bit of an inspection of the plane and then come to a conclusion as to what the cause is, because you can get some odd effects if, for example, one of the screws was coming loose holding the tailplane in place. All right, so I think it's time. We've now spent. Yep, Peter.
Could the asymmetry you spotted earlier in the auto tune results be explained by being on the wrong spline, and thus also the integrator?
Possibly. Yeah, I haven't really looked into the effect of either center of gravity being wrong on that asymmetry. I think that asymmetry is one.
There is another way to determine if the center of gravity is too far forward, and that is if you've got an airspeed sensor. If it needs a lot of up elevator when it's flying slowly, but significantly less when it's flying fast, then it's more likely to be a forward center of gravity.
Right. Okay. Yes.
Right, because that's one of the characteristics.
Yes, so we could plot, we could plot cton.as, which is our the airspeed that it's flying on, and aetr.elevator like that. And we could have a look at here. So in this auto mission, so here he's flying, it's a bit hard to tell because that's the auto tune. We'd have maybe this part of the flight, we might be able to tell something. So at lower speeds here, he needed more at higher speeds, he needed, the elevator was down at like, it's always way high, but it's less elevator at these higher speeds. But it's a bit hard to tell because it's quite noisy.
I can see the elevator, and you expect a stable airplane will require more elevator to fly at a slower speed.
Right.
And less to fly at a high speed.
Okay, so let's go and have a look at the actual question that he posted. So one of the things he wants is that it's landing 10 to 20 meters to the right of the landing target. Okay, so let's go and have a look at this auto part of the flight. So we'll just concentrate on this auto mission, and then we will, first of all, I might go and have a look at the attitude control for this part. So here's where he's doing his auto mission, and we want to concentrate on the part where it's coming into the landing here. So if we now use the little trick and scroll it here, we can see that the little snake, so he's coming in there, and so this is the little snake here coming in, and coming in there, he's going through waypoint 6, then coming up to waypoint 7, and the tracking here is quite reasonable. If we have a look at the distance here that is off, so he's off there by about 1.2 meters, which is, you know, not bad for a little foamy. And so he's coming along there, and then he starts diverging. So there's where it's getting interesting. About here, there's a couple of things that happen about this point in the flight. So he's coming up to this landing point here, and you can see that he was tracking really well up to this waypoint, and now he's tracking, here he's off by 8 meters, and it's just getting worse. Now, we also notice in the roll and pitch here that he is flying fairly level up to this point, and then he finds that he's suddenly not flying level, and it's just after he enters this final waypoint. So let's get people to have some guesses. What happens when you enter the final waypoint? What happens on an aircraft? Any guesses? Well, what I'll do is I'll go through, I've already had a look at this, so I sort of know what the answer is, but what I'll do is I'll go through the process of how you would have a look at it. So I would tend to look at the N-ton, right? So we can have a look at the cross-track and the N-ton cross-tracking integrator. So he's running what's called the L1 controller. Okay, so the L1 controller is the fixed wing navigation controller. And it's one that it tries to converge you slowly across, right? And it's got this little cross-track integrator, which is basically, you can see that it's a little bit negative here. So it's during this earlier part where it's coming up to waypoint 7, it's just putting in a little bit of left lateral acceleration, left acceleration to try to keep it on track. And then here, after it passes that waypoint, it suddenly needs a lot more, right? Now, isn't that interesting? Why it's suddenly, just because it's in this last waypoint, it needs a lot more roll. So then what we need to do is we have a look at what's happening with his control surfaces, but we need to add one more control surface into this graph. And I'll take out the throttle and I'll put in AETR.flap on the right-hand axis. And so what you'll see is at the point where it suddenly needs more cross-track, what is happening is that's the point where he shoves the flaps on, right? And as he shoves his flaps on, over the next couple of seconds, he suddenly needs more roll. Now let's make sure he's actually got flaps. Param Servo Star ION. I mean, this type of aircraft does have flaps usually, and we can see that Servo 5 is type 3. Servo 5 is type 3, which is auto flaps. Yeah, that's right. So if we have a look at RCOU.C5, we can see that that's where his flap goes up at the flap slew rate. So what appears to be happening with his cross-track here is an asymmetry gets generated when he puts his flaps on. And so now that means I would suggest that he go and have a look at his flaps and he tries moving them in manual mode, right? Controlling those flaps and seeing whether in fact one flap is going down more than the other, right? Or they're coming at different rates, or they're offset, right? The flaps are offset a little bit, because what appears to be happening, it's running basically the same algorithm here as it's flying in this part, but it's deviating a lot more, and the difference appears to be his flaps. And so I would be suspicious that he's got an issue with his flap servos. Now, it's not a very long distance here. He's flying, what sort of speed? That's a distance there. I've just measured a sort of 150 meters, and he's flying. So that's coming in over like 10 seconds or so. It is interesting that the controller doesn't manage to bring him back. And in time, he could lower, if he could lower his nav L1 period. That's what controls the, he's got a nav L1 period of 17, which for a properly tuned aircraft might be a bit high. He could probably handle a bit lower, which would bring it in faster. But really the correct fix is to get rid of the asymmetry that's driving this, and to go and have a look at his flaps and work out why it's causing it to go off course there. All right. So I think that's the main question answered for that first log. And we're now 50 minutes into our chat and we've only had a look at one log. So are there any questions on that one before we move on to the second log?
There's the observation that that's actually flaps auto. So by the time he actually gets to look at the vehicle, the flaps have possibly fall themselves away again. So you won't
Indeed,
notice.
that's right. He'd need to add a flap channel as a RC option, a flap input channel, and then he'd be able to, in manual mode, apply the flaps and just check that it is in fact going appropriately and that there isn't an asymmetry in his flaps. But I suspect he'll find that there's some sort of physical asymmetry in his flaps that's causing this issue. All right, let's go to the next log. Now, the next one up we had was from Andre K. And so let's have a look at the original message from Andre. So this was this message here. He's saying he's flying this aircraft, and as the speed changes for a fast low pass, he's getting altitude errors become dangerously high. The GPS indicated altitude seems good, but the EKF and pressure-based altitude is vastly overestimating its altitude. So you really don't want to do low passes when this is happening. All right, so we can have a look at this. Now I'm going to start off by looking with Dev ID. And now this is a slightly older log. If I have a look at the log, it's 407. So this is one that I sort of dug out of the archives from a while ago. And we don't, in version 407, we don't have a dev ID showing up for our barometer, which is obviously critical for this message, but we can have a look at what graphs are available. And we see that it's got BAR2 and Baro. So we got two barometers, right, which is great. It's always great to have two of a type of sensor because they can, you know, cross-check each other. Although it's not uncommon that both, in the case of Baro, that both have the same error, particularly if they're situated in the same position on the aircraft. Okay, so let's have a look at what's happening with, again, our state estimation. I tend to bring up, as I said before, I tend to bring up a map and the EKF innovations. Let's have a look at the map here. And we can see that here's, again, with a slight problem with the grid lines here. We've been playing around with the map widget in Mav Explorer recently, and it looks like it's stuffed up the grid lines at this location. That's something for somebody to fix, or probably me. So he's having some fun here, nice round circles there in his flight, a bit of manual flight, a bit of stabilized, bit of cruise, RTL, all right. And so let's have a look at the sequence of his flying here. And let's have a look at which flight modes he's actually flying in. We'll have a look at his speed, and we can see that he takes off here in manual mode, then he does a bit of guided mode, and then into stabilized mode. He's got a bit of auto mode here, finally comes back and lands on an RTL. Okay. Now, some similarity to the previous log, he's got a bit of, particularly noticeable is the blue lines. The height innovations are a bit higher than normal. They're not high enough to trigger a warning in a ground station, except he'll have gone amber a little bit on his ground station at these points where he's, you know, briefly peaking above 0.5. And we can go and have a look at them in SI units. If we have a look at the position down innovation, then so the EKF is, you know, upside down. So it shows it's northeast down. So it measures innovations in the down direction. So this is the innovation position down, and this is in meters. So we're seeing some quite significant innovations here. So we're seeing innovations getting up towards, you know, 9.7, so getting up towards 10 meters of height innovation here. And so let's presume, we're presuming that, of course, that he's using the Baro for height, but he may not be. So EK alt source on this old version of the code, it's the EK2 alt source that determines whether he uses Baro or GPS for altitude. And in this particular one, he's using the barometer for altitude. Okay. And so he's using the barometer for altitude, and basically the other altitude sources, the GPS will being used for vertical velocity, and the Baro for vertical position, and of course the IMU for the vertical accelerations. So he's getting quite a large discrepancy that he's got here. Now let's have a look at whether these discrepancies are at all related to our airspeed. All right, so let's have a look in this part of the flight where he's got a nice range of airspeeds, right? So he's we've got our ground and airspeed there, and we can see that at higher speeds here, when he's pushing up to 35, 37 meters a second, this plane is really moving, right? He's you know, 37 meters per second. That's like 110, 120 kilometers an hour, something like that, maybe 120 kilometers an hour, really quite fast. And you can see that as he speeds up here, the innovations get quite high. Now let's have a look at whether the two barrows are agreeing. Okay, barrow.alt, and because it's this old log, it's bar2.alt. Okay, and what we can see is the two barometers are in fact in very good agreement here, right? And in fact have very, very similar noise. Okay, let's see what type of board this is. So this is a 3 IMU board, where the first IMU is an MPU 9250, second is LSM, third is MPU 9250. And if we look at the messages at boot, it's almost certainly a cube black. It is indeed a cube black. All right, so he's flying a cube black. Now the cube black has, I've got one sitting on my desk here somewhere. There it is, there's a cube black. So a cube black, both of the barometers are inside the cube, right? They're just on different buses inside the cube, which means they're both exposed to the same airflow. They're not really fully independent barometers. It's great for redundancy in case the barrow breaks, the bus, you know, the little connection to the isolated IMU breaks. Also, one of them is closer to the heater for the temperature the heating to keep a stable temperature. One's a bit further away, but they basically both see the same airflow over them. And so they're not really independent readings.
With all of the cubes, the barometers inside are measuring the pressure at the USB port. Effectively, that's the biggest hole into the cube. So effectively, that's where you're measuring the pressure, is at it's the flow location for that USB and SD access point. So if you get airflow past that, that can create turbulence, and you can see some quite noisy measurements. If I've got one exposed to the airflow, I'll put a little bit of tape over that hole if I'm flying it in a copter exposed to airflow.
That's a very good suggestion. So what we're going to do now is I'm just going to plot the barrow.alt and the GPS altitude, and I want to zero the GPS altitude for on the ground. We can see that the GPS altitude is starting at about 367 meters, which is consistent with what we see on there. So I'm going to subtract 367 and plot that against the barrow altitude. Just occasionally these graphs take a while to come up. There it is. Okay, so what we're seeing is we are indeed seeing quite a significant difference between the barrow alt and the GPS alt. Now let's put the cton.as, the airspeed, in fact it might be AS in this case, in this log. These older logs, it's called ASPD. All right, so here we have the discrepancy, the red and the green lines, the discrepancy between our GPS altitude, and there we have our airspeed. Now the interesting part is in this part here, where he's in stabilized mode, and that graph's finally popped up, where he's in stabilized mode and he's flying at, he's diving up and down and changing his speed quite radically.
In fact, if you plot the GPS altitude minus the barrow altitude, I think that correlation will show up.
There you go. Clearly. I'll do GPS altitude minus 367 minus the barrow altitude against the airspeed. So we can see the difference between the two. And what we see there, nice big graph there, we see two things. First of all, at higher airspeed, his barrow gets very, very noisy, right? Look at this baro altitude going, you know, crazy, right, at higher air speeds. As he slows down, the baro, settles in and is perfectly happy, and he's getting a lot less discrepancy. So what we're seeing here is sort of a, I guess you call it a Venturi effect, where he's getting sort of airflow past the side of the cube here, past that little USB port. And as he gets high-speed airflow by that, his baro is changing quite significantly. And and what we're seeing is it's getting a higher altitude estimate because it's got lower pressure, because it's sucking the air out of the cube, right? As the air is rushing past, it's sucking it out, lowering the pressure, so which means it thinks it's a higher altitude, and he, you know, gets to close to the point where he could crash into the ground.
Yeah.
So a little piece of sticky tape, as Paul suggests, would very likely solve that. Or it could be, you know, the holes going into the fuselage. There's all sorts of things, but the simplest thing for him to do.
We don't know what that looks like. Is it exposed to airflow? It's possible that there's that the fuselage, because if it's inside a fuselage, it sees the pressure inside the fuselage, and if there are openings, sometimes you get a point where some planes will get to a certain speed, and you'll start to hear a whistle from little gaps and slots and things. And although a whistle can sound pretty nice when somebody's diving, that's a whistle indicates a very strong acoustic oscillation or pressure oscillation to get a strong sound, and that can actually be picked up into the baro. And the worst thing is, because it's such a high frequency, it can actually cause the baro measurement to what they call alias, which is if you put in a higher pressure fluctuation than the baro can sample, it can cause unpredictable offsets in the baro. So yeah, unfortunately, this is something where it needs to be fixed in hardware. We can't really fix this in software.
Exactly. Yes. So this one, he probably needs a little piece of sticky tape to solve this problem, and he would then find that his baro reading be a lot more consistent. Now, of course,
it'll be less. You may be able to stop that noise. We don't know the setup. It could be that he needs to block holes on the fuselage, or
could indeed
open up other holes to equalize pressure or do something. We don't know.
Yep. So that's our likely cause. You can see this, that it very much is airflow affected. Let's have a look at some of his other things while we're here looking at his log. Let's have a look. There was one of these logs. Yes, this particular one I think was the one where I noticed that his compass was a little bit odd. And so we can see that his first compass here, the first one that he's actually going to be using, is this priority ID 1, which is a UAV CAN compass, okay, which is all good. But one thing we see that's a little bit odd is he doesn't have any compass offsets for this. So he's neglected to calibrate the compass since he installed this UAV CAN compass. All right. Now we can see that if we're dived into our state estimation a little bit more, then we would have seen the impact of that. And what we can see is what the EKF is learning for the mag body field and the mag earth field. So what we see is the EKF dutifully learnt his compass calibration when he was flying. Right. So in other words, he hadn't calibrated it at all. And within very, very rapidly, it learnt these offsets. But it does mean he could get some slightly odd effects at takeoff.
Yeah.
So,
something to point out is that these are biases, which means if you wanted to take these, you could take these and use them as offsets, but you'd have to flip the sign.
Indeed, you'd have to, but we can do better than that. So I thought I'd use this opportunity to show how to do a calibration. And we can see that he's flying around in these great big circuits, right, which is wonderful. So what we can do is let's just pick one part of this where he's flying in these nice little guided mode circles, right? And so we're going to go in here, and we can see his attitude control as he flies in here. That's all fine. So there we are, concentrating on the part here where he's flying in this circle. And so that's flying for several minutes in circles. what I'm going to do is go and calibrate his compass for him, right? So we can bring up under this tools menu a thing called MagFit, okay, which is a flight log based compass calibrator. Now, so I can ask this to estimate the correct values for the offsets, etc. Now I'll just see whether he's got battery. He actually doesn't have a battery monitor set up. If I have a look at the battery monitoring, he's got all of them zero. So we don't have the current. We don't have a current sensor, which means we can't do this bottom part of the one where we actually estimate the motor interference. If you've got a current sensor, you can actually use the flight log to estimate not just the compass offsets and diagonals and off diagonals, you can also get it to estimate the interference from the motors, from the current flowing from the battery into the motors to get an even more accurate compass calibration. We can't do that on this because he doesn't actually have a battery monitor set up at all in this aircraft. But what we can do here is I'll do this reduction here to reduce the number of samples because this process can be quite slow, and I'll ask it to estimate offsets and ellipticals in this flight. So what we're doing is saying, please estimate what the correct offsets are and what the ellipticals should be, and let's go and run this. Now, there's only 568 points here, so it won't take very long. Normally you'd run it with a bit less reduction here, but I'm just trying to move things along a bit more quickly. All right, so there we have it. So it's now, I'll just explain this because a lot of people find these graphs quite confusing, and it is very, very useful. So if you've got a flight log and your compass isn't quite right, you can use this tool to get really good compass offsets. But these graphs bear some explanation. So the top graph is what happened in his flight, and we have 6 lines for each of the X, Y, and Z. X is to the front, Y is to the right, and Z is down in body frame. So on our little flight controller here, so X is along that way, Y is that way, and Z is that way on the flight controller, right? So these are the blue line here is the uncorrected X. So this blue line here is the value that his sensor gave in flight, right? So it's the actual reading from the compass in flight. The yellow line here, the expected X, is the value that we would have expected from that sensor if the field follows the world magnetic model for that location on the Earth's surface at the roll and pitch and yaw estimate that we had during the flight. Now, this assumes that our roll, pitch, and yaw was okay. And so we can basically use the world magnetic model to predict what the correct fields would have been, right, in the flight. And it interpolates in a table, and it tends to be reasonably accurate. It's pretty good, the world magnetic model. So what we see is that there's quite significant discrepancies. We can see here, for example, it's off by nearly 200 milligauss. This is milligauss vertically. And we can see that, for example, on the y-axis, it's off by 150, 200 milligauss here. And the z-axis, it's off by an enormous amount, right? And really does quite badly. Okay, so then what this fitting tool does is it goes and estimates new compass calibrations. So these are the new calibration values that it's come out and estimated. So these parameters can be directly loaded, right, into the flight controller ready for your next flight. And it shows you also what the current values were, the values you had in the flight, and these are the new estimates in a vector form, and these are in the parameter form ready to be loaded. And you can see that his original ones were 0. Right, so he had neglected to calibrate that compass. I'm actually surprised you didn't get an arming warning about that. I thought we checked all zeros. All right, so this second pane is what would have happened in his flight if he had been using these new parameters. Okay, so in other words, if he'd set those parameters, then he would have got, you see these 3 lines now line up very nicely. Okay, so his X, Y, and Z all line up beautifully. Now you've got to be a bit careful. You do get a little bit of a problem of garbage in, garbage out, and an overfitting sometimes. So you have to make sure that the aircraft went through a sufficient range of angles, particularly in yaw, but also preferably in roll and pitch, for this to actually be worthwhile. And in this case, I'm quite happy with it. He's circled around, you know, quite a bit, and he's banked a fair bit, and he's done some flat. So that's quite sufficient. So I'd be reasonably confident that this fit is a good one. And you can see that there's no real anomalies all the way along here. The fitted values, the corrected values are matching the predicted values very well. So I'd be reasonably confident that those parameters that are suggested are good. Now, this third graph is what really tends to confuse people. So I'll try and explain that. The yellow line here is how much difference this would have made to the yaw in degrees. Vertical scale here is in degrees. How much difference between what the EKF estimated as the yaw and what the raw compass would have given with the corrected values. And you can see it's almost zero, right? And that's because the EKF did a wonderful job of estimating the corrections in the flight, you know, regardless. So it basically very, very quickly fixed things up. And in fact, putting in these values would not have affected his flight very much, except in the first little bit before the EKF had learnt them, right? The takeoff could have been, runway takeoff could be a bit odd because the EKF can only learn the values once it's got some movement, right? But it didn't, for most of the flight, certainly this up and away flight wouldn't have made much difference. This blue line is the amount of difference it made to his yaw estimate from the raw, just the compass without the EKF corrections. So this is comparing the what's called the tilt corrected compass yaw estimate with and without these parameters applied. And you can see here, the difference is huge, right? In fact, it was 150 degrees. It actually wrapped at 180 at one point, which means the compass was pointing entirely in the wrong direction, right? And the EKF coped with that and learnt the right values and did. So there's a real testament to the EKF's ability to cope with a terrible compass. He had really, really bad compass offsets here. And so he should go and apply these new parameters like that. Or of course, he could just do a compass calibration on the ground and it would have also fixed it. But it was a good example, I thought, for this log of, you know, just how well the EKF can do in fixing, you know, compass offsets, and also how to use this tool to improve compass calibration. Now, the EKF does an admirable job, but we shouldn't rely on it. I don't recommend flying with an uncalibrated compass. Because, you know, although it did very, very well in this case, and it usually does very well, we have seen cases where it can't manage to get a good convergence at some critical point in the flight. So don't just don't use this log as a suggestion that you can fly without calibrating your compasses. But particularly useful for planes that have significant motor interference, which we couldn't do on this log because of lack of battery, because we don't have a motor interference tool for plane that you can do on the ground. We don't have a way to run up the motors and automatically calculate the motor interference. So if you've got a fixed wing aircraft and you want to get that motor interference filled in, the best way to do it is with this tool, and you just tick this little CMOT thing and it will estimate your motor interference numbers and will put them into the calculated parameters. You have to make sure that you include in the part of the flight that you're matching against a part where it does have significant changes in throttle. Otherwise, it you know, can't estimate it if it's always at the same throttle value. And I should note, the data that this fitter fits over is the place that you last zoomed to in the flight, right? So that's why I ended up with a bit less data here, because I zoomed only on this part of the flight. You need to pick suitable areas. So typically you don't want to include the part where it's sitting on the ground, where there might be a big magnetic, you know, thing under the ground affecting the aircraft. You want to make sure it is actually up in the air away from major magnetic sources. And you zoom into that part of the flight on one of these graphs, and then you open this tool and it will pick up the part of the flight that you last zoomed to. It remembers the last zoom location. All right, so any questions there about this flight log? All happy? We'll move on. Okay, so we got through that one a little bit more quickly than we did the second one. So the third log here is in some ways my favorite type of log because the pilot found a bug. And this one was very recent. It was only found yesterday, and the pending PR to fix it, bug analysis, thank you to Leonard. And then I did a patch to fix the bug with Leonard's help. All right, so this aircraft was a H-wing, which is our vertical, so it's a quad plane. In fact, I've got this plane, one of these planes sitting on my desk here. So you can see that, hard to angle cameras correctly. So there you go, this is H-wing. It doesn't have its wing extensions. The wing extensions are sitting on my table over here like that. But this is a slightly unusual aircraft in that it's a tail setter quad plane. So it takes off vertical like a tail setter, but it doesn't have any control surfaces. So it's only got the 4 motors for stability. So you run the motors all the time. You can't glide at motor off with this. If you try that, it will plummet into the ground very quickly. Has very, very poor glide characteristics, but it's a fun aircraft. Okay, so if we have a look at the report we got back, so he was comparing it to flying the same aircraft on PX4 because this aircraft has a bug in that it comes with PX4 installed, so we have to fix that, of course. And so now it's running ArduPilot, and this was one of our brave testers of the ArduPilot port to this aircraft. And is saying it's great, major improvement compared to the PX4 stock firmware. But he said one odd thing, some odd things happened when transition out of fixed wing. It shot upwards in Q hover and Q loiter one time to 400 feet, even I was holding down stick. So in other words, he was going from fixed wing fly-by-wire A mode, and he flicked to Q hover mode, and the aircraft went whoosh, right? And it climbed. Now, you somewhat do expect that. I mean, if you've got a aircraft, a tail sitter that's going in fixed wing flight forward, right? And then you put it into a vertical flight like that, it's got a whole lot of kinetic energy, right? So, you know, half mv squared, so its velocity squared is your kinetic energy. And you're wanting to get it into hover where it's now just sitting there still vertically, right? Well, it's got to turn that kinetic energy has got to go somewhere. It could go into noise and, you know, drag and heating the fuselage, but not much is going to go there. Nearly all the energy is going to go in potential energy, and it's going to climb, right? Because it has to turn that kinetic energy into potential energy, and potential energy goes as the, you know, mass times height. So it's linear with height. So basically, if you've got a high-speed aircraft and you put it into a hover, you expect it to climb. The question is how much it climbs. And so he noted that it climbed quite a lot. So let's go and have a look at sort of the state estimation and things like we normally do. So let's start with our basics. So here he is flying around in what looks like a lovely, nice, big, flat prairie. And he's flying mostly in fly-by-wire A, but he's doing the takeoffs and landings as this is a tail sitter in Q hover and Q loiter. Let's see so it's a dev ID. We can see that it has an airspeed sensor, which is an MS4525. Interesting thing about this airspeed sensor, it doesn't have, I'll just show you close up on my aircraft what it looks like. If I turn on my light here, can you see that airspeed sensor there? Or am I pointing in the right? You see the little plastic, that little thing? That's the airspeed sensor, right? It only has one hole in it for the dynamic port, which is the, you know, getting the air ramming in. And the other tube from this MS4525 is just loose in this camera area. It's loose inside the fuselage. So the static is just coming from inside the fuselage rather than having a separate static port. Okay, so he's got this MS4525 airspeed sensor. He's got an MS5611 Baro. He's got his two IST, just one, sorry, IST 8310 compass, and then he's got 3 IMUs. All right, so let's have a look at how we're doing in our state estimation. Okay, so we can have a look at our first lane state estimation and our second lane state estimation. Now, I particularly wanted to have a look at this state estimation because on my aircraft, I had noticed that the second lane tended to be a lot better state estimation than the first. Now on his, it isn't. On his, this first lane and the second lane are actually incredibly similar, right? So very, very similar. So the 2 IMUs are performing very similarly. So that's interesting that my one is a little bit different characteristics and tends to have has a better second IMU, even though they're exactly the same flight controller. So that's sort of interest to note that, and then we'll, might have to investigate that later as what's different between the different ones.
That's not that unusual, actually. I mean, they're not a screened part by the invent sensor or whoever makes them.
Yes, they could be. And one of the things I wanted to add, Paul, was an EK3 primary parameter, so you could pick which is your primary IMU.
Yes.
And so it will lock on to, in my case, I want it to be the second IMU, so I'd set EK3 primary to 1. So I'm planning to do a PR for you to just have that. It should be a very simple patch to be able to select which one is the one that it locks onto at boot, rather than waiting for it to change IMU mid-flight. All right, so our state estimation, we're getting, now one of the interesting things I note in this log is notice the SVT is 0 the whole time. That's our true airspeed. That would seem to imply that it's not using that airspeed sensor. Let's have a look, which it should be. And we have airspeed use as 1. All right.
Yes.
Let's see if it actually found this airspeed sensor. It could be that it was flying the wrong speed. So airspeed.airspeed. Yes, he definitely had airspeed. Let's see what the airspeed fly-by-wire min and max are. ARS fly-by-wire min is 8, fly-by-wire max is 25. Yes. So that's actually a puzzle here. His airspeed is in range. It's in the range that we want, between the minimum and the maximum. And yet we're not seeing any true airspeed innovations. Over to you, Paul.
Now, okay, so this is where the EKF relies on being told by the rest of the ArduPilot code, are you a helicopter? As in, are you flying like a multi-copter or a helicopter where you can't use the airspeed, a multi-copter where you can't use the airspeed sensor because you could be flying sideways or backwards? Or are you flying as a plane?
Yes, I know what's happening then. Then what's happening? Yes, you're exactly right, Paul. Of course. Sorry for cutting you off. We've got a bug. So this plane runs a Q assist permanently, right? Because in fixed wing flight here in this fly-by-wire A mode, right? It's flying in forward flight, but it's running the quadcopter control loops to control it in forward flight.
Yeah.
Right. And we set that flag based upon whether the VTOL motors are active on a quad plane, which means it's always doesn't think it's forward flight. Now that's going to ruin our side slip fusion. And it's also going to ruin. You won't have
side slip fusion running at all.
That's right. That's right. So that actually means this log has found 2 bugs.
Yeah, and have a look at the the wind estimates on the EKF, and it's probably not doing wind estimation.
Yes, it won't. It probably isn't doing wind estimation as well. So let's go and have a look at the EK3 wind speed and direction estimation. It's a very new type of aircraft for ArduPilot. So yeah, no estimation at all of our wind. All right. So
it thinks it's a hovering vehicle the whole time, all the way through.
That's right. So we need to. In ArduPlane, quad plane, fly forward. I'll just put a note to myself. Fix fly forward setting for full-time quad tail sitters. All right, little note in the code there that I need to fix. So that's a bug, and that will improve our airspeed estimation. It will improve our dead reckoning a lot when we are trying to come home if GPS fails, which is important because I have heard that the power wire going to the GPS in this vehicle may be a little bit dodgy. Some people have said they had to fiddle it to get GPS. So if that fails in flight and we don't think we're in fly forward, then our ability to dead reckon would be, significantly reduced. And well, it'd be really crap, basically. So interesting that bug shows up. Apart from that, we're seeing a little bit of magnetometer error, a little bit of height innovation here, and we could have a look at how significant that is in terms of the actual position down innovation. All right, we're seeing the height innovation noise here of like 5 or 6 meters, quite high, and that's sitting in fly-by-wire array. So we're probably getting a little bit of sort of Venturi effect and noise as well. Yeah, it just means it's just the design of the fuselage and the way the airflow is. It may not be completely perfect there, and much higher noise there in forward flight than in hover. All right, so let's have a look at the actual issue that he raised, which is that one time he went from fly-by-wire array to Q hover and it went up a lot. Okay, so let's have a look at the start off with pos.rel home alt, and we'll actually show the cton.as, the airspeed. So what we've got, oops. All right, so here we are, we've got our airspeed here, this green line here, and he's rocketing around at sort of 18 or so, not that fast, actually sort of 18 meters a second, changing his speed quite a bit actually in fly-by-wire array mode. And then he transitions here, this red section here, he transitions to Q hover. And so here he is transitioning to Q hover, and his airspeed comes down as you expect, right, as we're losing our kinetic energy. And then we are gaining a lot of altitude here. So his altitude in meters went from here at the start, his altitude was down at 40 meters, and he ended up getting up to 110 meters. That's 70 meters. Now we could work out the half mv squared compared to mh and work out whether that's a reasonable height. And indeed, that's gaining more height if you work that out. Maybe Paul's doing it on his whiteboard in the background. It weighs about 1.5 kilos, Paul, I think.
We don't need the mass, but I can, yeah, that's.
Yep, we could easily say that, or we could even plot the kinetic energy versus potential energy. Why don't I show that? Let's show off the capabilities of, so we can show off, so we GPS.speed squared, and we want 0.5 times 1.5 times that. That's our kinetic energy. And our height, which is going to be our, well, let's just do our relative home alt. So m times h, so 1.5 times h. All right. And let's show, what we can do is show the sum of those. Our kinetic and potential energy should stay about the same. Okay. And what we're seeing is, let's see. Yeah, so here it's gaining energy, right? So it slows down, but it's gaining energy here.
Yeah. Yeah. Even if it was 100% energy efficient in the conversion, it shouldn't gain more than about 20 meters of height.
Indeed, that's exactly right.
Way more than that.
Yep. Yep. Okay, so now we need to look into our controllers, and this is I chose this log partly to show how do you dive into the controllers. So this was the process that I went through with Leonard. I spent about an hour looking at this, and I made some progress but didn't get the final solution, and then Leonard came along. Now, so what I'll do is I'll just show you some of the key graphs. So first of all, we've got this climb rate graph, right? And I'll just go into this part of the log here. And we can see that this is where it's transitioning from fixed wing here, and it's coming up and it's climbing. Now, one of the things to know about the VTOL controllers is we're showing here the DCRT, which is desired climb rate in meters per second, right? And CRT, which is our actual climb rate. So this actual climb rate is coming from the, I'll just mark myself as a way here in Skype. This is coming from the EKF, and the desired climb rate is coming for our controllers. Now, notice the desired climb rate is positive, and we're transitioning with fairly neutral sticks. Let's have a look at his sticks, what's happening on his RC inputs. And in fact, he's demanding descent here on channel 3. If we have a look at RC map, and channel 3 is throttle. And in fact, he's demanding neutral at the beginning in hover, then he's demanding it, saying, please come back down. All right, and yet it's climbing. Now, one of the things to know about these VTOL controllers is you never see a too large a gap between them, because the controller always sets the desired to a maximum offset below or above the actual, right? So even though we're actually asking for no climb rate at all, the desired from the point of view of the pilot is a flat line here, right? But the desired from the point of view of the internal height controller is, it gets dragged upwards by the actual. So what is important here is the fact that the green line is below the red line, meaning it doesn't want to climb this fast. It wants to slow down, okay? And yet it's not, all right? So we can start having a look at this message called the PSCZ message, which is position speed controller Z axis. Z is the up down part. And in fact, Z is up in this message, whereas in the EKF and a lot of other places, Z is down. So it can be a little bit confusing. Now we've got a whole bunch of fields in this message. We've got the position in Z and the target position in Z. We've got the velocity in Z, that's here, the VZ, and the target velocity in Z. And then we've got the acceleration in the Z axis. And then we've got the target acceleration in Z, and we've got this thing called the desired acceleration in Z. All right. So let's first of all have a look at PZ and PSCZ.TPZ, which is our position Z and target position Z. And if we loop in, you can see here that the target position is being dragged upwards by the actual position, right? And that's this characteristic of the controller. It never allows it to get more than a couple of meters, typically depends on your parameters, a couple of meters behind. But basically, because the target is always below the actual, that means it doesn't want to climb as fast. It wants to go down, right? It doesn't want to be this high, but it's not managing to slow down. Okay, so something's gone wrong. We know that it's not that it was wanting to climb, so it's not a bug in the demanded height, it's a bug in a lower layer of the controller, and it's a nested PID controller where it's got a position controller for height, or a height controller, then it's got a vertical velocity controller, then a vertical acceleration controller. Okay, first of all, our position controller is saying we want to be lower. Now let's look at the velocity controller. So let's look at VZ and TVZ, right? And we can see here, we're getting a little bit of odd thing with some stepping in here, right? But the key thing is that at least as far as doing this major climb, when it's going, when it's climbing up here, at least at the first part, the target velocity is below the actual velocity. It actually does go a little bit higher than it here, right? It goes up, so that's a bit of an anomaly. Most of the time, the target velocity is below the actual velocity. Okay, let's have a look at our accelerations. Vertical acceleration and so AZ, which is our vertical earth frame acceleration and our target acceleration. Okay, so let's go back and just zoom in again on this part. All right, now there's a few things that are interesting here. First of all, we see these numbers are in meters per second per second. Okay, so these initial numbers here, that's 2G. That's a lot, right? For a plane, when it's going from forward flight to vertical, it's going whoosh. The other thing is, notice there's this gap. Okay, so it's in fly-by-wire array here. That's this blue or mauve or whatever you call it section. And then there's the red section here, or pink section, where it's gone into hover mode. But you'll notice that it doesn't start giving data here. There's no data points. It doesn't start controlling the height until a couple of seconds after it flicks to hover mode. And that's because of the way the transition works. So it's coming along in fixed wing, and the first thing it does when it transitions is it starts bringing the nose up under fixed wing control. And that's because this controller was inherited from controllers where when you're in high speed flight, it's your control surface, your elevons that are dominating, right? And then the elevons bring you up, and then once you've started to slow down and come up to a certain angle, it hands over to the VTOL controller, which brings you then to the last part. So that's what we're seeing, this gap here, where it's not starting the vertical controllers until it gets to this point. And so we can see here that the point it starts the vertical controller, the vertical acceleration is really quite high, right? Let's have a look at all of our Z parameters. So I'm going to go Q star, Z star. That's all of our Z parameters. And the key one here is this Q excel Z. Now, Q excel Z is the maximum pilot controlled vertical acceleration in centimeters per second, which is 250, which is 2.5 meters per second. So in other words, we're saying that we don't want vertical acceleration in pilot controlled mode like Q hover or Q loiter over 2.5 meters per second. Here, we are starting the controller when we're at 20 meters per second, right? Which means 2G, whereas we don't want to go more than quarter G. Okay, so now we're starting to see an inkling of what the problem might be. We're initializing this controller with a high vertical acceleration. Now let's go and add into this the PSCZ.DAZ. Okay, now that shows what's happening to what's called our desired vertical acceleration, which is what gets initialized when we start the controller and then slowly bleeds off until it settles in. So this is the part that prevents it from doing sudden jerks vertically, right? So this is what prevents it doing, very, very sudden vertical controls where you go whoosh, whoosh, like that. But it gets initialized here at the start to the actual vertical acceleration at the start. So what's happening is we're coming along, we put the nose up. That initial nose up leads to a very high vertical acceleration, because if you tip the nose up to 45 degrees when you're going along at 80 kilometers an hour, you are going to accelerate up vertically a lot. And then it hands over to the vertical controller and it initializes the vertical controller. That's this point here, initializes the vertical controller with our current vertical acceleration, which is this 2G. And it says, we want to start with that point and then start the controller. But look how long it takes to bleed this off, right? So it takes it like, what is that? We're starting at 34.59 and we're ending at 05. So we've got 5 seconds before it bleeds down this desired acceleration, okay? And so that means that it's going to initially, the controller is going to be aiming for this acceleration initially, and it's going to be putting on this target acceleration, dragging it up. So here's the actual acceleration, and it's dragging it up. The target is over the actual and saying, go, 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 I want to accelerate, right? And it's very high throttle and pushing the aircraft up. Okay, now it can't actually achieve this acceleration. It can't maintain 1G vertical acceleration or 2G initially, right? It just doesn't have enough throttle to do that, but it's trying to do as much as it can to do what it was told to do. So the bug in this code is this initialization point. And so often it's our initializations that are a little bit off. And I'll show you the bug fix that Leonard and I did yesterday, or really Leonard, I put in the actual patch, but Leonard was watching over my shoulder. And that is this PR. And let's see, I might have actually already merged this because Leonard approved it. Let me have a look at merge. There it is, fix Z controller initialization bug. And so we're crediting the person in the forums who found it. And the bug was, the most important bug was this line here, where when it was initializing the Z controller, it was just using the current acceleration, but it wasn't constraining it to the limits for this mode, right? So if you had a vertical acceleration of 50 meters per second, it would have started off the controller at that 50. And because it's jerk limited, it's trying not to change the acceleration too quickly. That means it's going to go for all it can for a very long period of time. So what we need to do is, first of all, constrain that initialization when we come and we initialize the Z controller to the pilot limits here, right? So that we're not starting with this ridiculous value. And the second thing we were getting wrong is we should have, when we were calling this special function, which is this no descent function, which is used when we're transitioning for a tail sitter in particular, where we're wanting to go, forward flight upwards, and we want to actually initially not descend, the max here was wrong. It should have been max of 0 and the desired not max of 1G, because this was providing a minimum of a 1G vertical climb when we transition in a tail sitter. And the difference this makes, this bug was entirely reproducible in the simulator. And so we've got a nice little simulator of this exact aircraft. And it also reproduced these 400-foot climbs after transition at high speed. I had, not chased it down when I was initially developing it, excited to get the model out there. And once I put this fix in, instead of going up by 100 meters on a transition, it goes up by about 7 meters, which is much more reasonable. And so the aircraft does not climb like crazy when we have this transition to vertical flight. And so now, of course, we've got a second bug, which is we notice that our true airspeed innovations are always 0, meaning we're not, for this particular type of unusual aircraft, we're not setting we're in a forward flight mode flag correctly to the EKF, which means we're not taking advantage of our airspeed properly, and we are not taking advantage of things like side slit fusion and wind estimation and all the other good things you get by having wings. So we will enable that as well. So I'll need to do a patch for that.
Question: You're obviously, you're constraining the initial values here, but where's it getting those? The 2G vertical acceleration.
It's getting it from the current acceleration. So it's just the IMU, and it's actually the blended earth frame acceleration, which comes out of an EKF estimate, which is really just a smoothed and blended, estimate rotated into earth frame. So it's basically your IMU. It's your Z.
So the vehicle really was at that point accelerating.
Oh yes, because remember that it doesn't engage the vertical controller until after it's already put its nose up in fixed wing mode, which means when you put that nose up, it does climb at 2G initially for a very short period of time, right? So if we look at those IMUs, we look at the raw IMUs at this point of the flight.
Yeah, there'd be a faster way to transition if you were really brave.
Yeah.
You just turn the motors off, wait for it to drop, and then switch it into hover mode and hope Leonard's controller can catch it.
Indeed, and one of the things, I haven't gone quite that dramatic, but I have been adjusting the parameters for this model for an auto landing, where it's coming back and doing the back transition auto landing. And I found basically this model can fly at, there is no lower end on the stall speed. it can fly in fly-by-wire mode at all the way down to you know, practically 0 speed, because it just puts the nose up and up and up, right? And it can then come in at very, very high angles of, you know, high pitch angles, high deck angles. So I've now set the text land speed really low, and which means on the final approach for landing, it does drop the motors down, way down. We don't drop them to 0. We have a throttle minimum, I think, of 15%. So you keep some attitude control, right? Because otherwise it's not quite balanced perfectly, and it does tend to nose into the ground. So you need a little bit of throttle there to allow it to have attitude control. But that means you can slow down a lot on the approach, and that means it actually, for those auto missions, it actually only gains about 3 meters on the back transition. But in this case, the pilot was flying it along at 20 meters a second, which means you don't get that opportunity. But here you can see
there's a lot of scope for doing strange things on landings with these things. I mean, roll through 90 degrees and then yaw through 180 degrees.
That's right. You could roll it over to be knife edge and then pitch it up like that if you wanted to. There's all sorts of things you could do, indeed. It'd be a good thing to play with. And probably at a bit high height when we do that, you know, so we've got plenty of time to recover. But you can see here what happens during the transition, right? This is the accelerometers, and the ZXL really does, you know, hits 4G there momentarily. So, you know, it gets a very, very strong acceleration. And the rotated acceleration, the earth frame acceleration, isn't quite that high. We do log that somewhere. Where do we log the earth frame acceleration? Qton, is it in Qton? We do log that attitude. Might actually be an attitude. Error RP. AEK. No, that's the active EKF. Somewhere here, if I can find it, there is in fact the earth frame ZXL is, can I remember? CTON, where did we hide it? Peter, can you remember where we hide that?
CTRL, not CTRL.
No, we've not got a CTRL.
Oh, well.
I'll have to go and have a look in the log file. So if we go in libraries APAHRS and we look at the name of the function.
This is an older version of the code though, isn't it? So
yeah, no, this is new. This is the other log.
This is the new one. Okay.
And so the logging here is, where's the logging? AHRS logging, APAHRS logging. It is in the, it's in the rate packet, graph rate dot. And there it is, A out. No, it's not A out. It might be just A. Rate out dot, where is it? A out, A des, P out. Yes, I think it's just rate dot A. We'll have to look at these messages. So this is the rate message. And so the rate message is yes, it's rate.a. There it is. So this is the earth frame ZXL. And you can see that it was sitting at about just above 2G when we engaged this controller, right? So it was really accelerating vertically. So this is the earth frame Z acceleration. All right, so that was 2 bugs. I love logs where we actually find bugs and then we can get them fixed. And and it's partly why it's often worth looking a bit further than just the issue that the pilot raises, because we often find new things. Like, for example, I hadn't even noticed the first time I looked at this log, the fact that the innovations on the true airspeed were 0, meaning it wasn't fusing airspeed. And so that's a bug we haven't actually got fixed yet. All right, so we're coming up to the end of our 2 hours, and I think this has been a lot of fun. I might stop my screen share now and back to chatting with people. So are there any questions at all or anything we want to go into the last few minutes?
Andrew, you mentioned that you use a simulator to validate your bug fix, for the latest case.
Yep.
Which simulator do you use?
For this particular one, I use RealFlight. I could even fire that up if you like and show you what it looks like. People want to see that. I unfortunately, the main problem with these simulators is when you do screen sharing with these simulators, that the simulator is on my Windows box and I'm making the call from my Linux box, right? So what I can do though is I can fire this up, and what I'll do is I'll do a slightly strange things with and I'll do a slightly strange thing where I'll actually use a different screen sharing thing, and then I'll connect in here. So if I'll go and share my screen again here so you can all see, and I'll do a 2-stage screen share where I share my desktop. I'll just start up RealFlight here and wait for RealFlight to start up on my Windows box. And it's just starting at the moment. And there it is starting up. Okay, Windows. And I share on my... So there's lots of different simulators, and which simulator you use is sort of a bit dependent on the situation. For this particular vehicle, you can see here that I've now got this simulator because the ArduPilot is not connected to it. So this is what happens if you have no flight controller at all on this vehicle. You guys are seeing that okay? I might be best off sharing just that window, in fact. It might give better result. I might share again. So share, if I go share, let's see, Chrome whereby share. All right, can you guys see that window okay now? Oh, actually, no, I will share whole screen because you want to see me controlling it with ArduPilot. So let me share my whole screen. All right, so what I've got there now is RealFlight sitting over here. And then I will go into my RealFlight and I will go, I've got my parameters on this Foxtech and I've got a particular branch that I'm using. And so I'm going to connect with ArduPilot by running sim vehicle with various parameters. And it's going to connect across to this guy. And then I'll just reset the vehicle so that it's vertical. So there's the vehicle sitting on the runway. All right. And so now what I'm going to do, I'm going to put it into Q loiter mode. So it's now, you can see up here, and I've got, there's the map. I'll put that up there. So we've got something that we can see here. And I'll even grab a mission. So there's a little mission for it to fly. And now I'm going to arm the throttle on this vehicle and I'll fly it. And now it's going to be a bit jerky because with the screen sharing, but there it is, happily flying like that. And I'll just yaw it around a little bit. And so you can see if I bring it a bit closer, you'll be able to see the nice ArduPilot logo that we've got. Brandon is our modeling person who's done these nice models. And so there it is flying in RealFlight. So it's actually a pretty good model of the aircraft. It looks just like the aircraft, and it is oscillating slightly there. When I'm screen sharing, I end up with some odd transport. So I'm running over a network, like a gigabit network here. And I'll just close off this little binocular window. But what I could do now is I could tell it to do an auto mission. All right, so I can go and I'll take it there and I'll bring it back down and land it. And I could even show you the pre and post the bug if you like, but let's go and put it in an auto mission. There it is going to do an auto mission. It'll take off and fly off into the distance. And this is where I probably do need the binoculars like that. So there it is flying off into the distance and flying around our mission. And we can see on the map here, it's coming up to the second waypoint. Going to fly along there. And then when it comes back to the end here, it's going to, you know, go back to hover and land vertically. All right, so it's a very useful tool. It does have downside. It's not lockstep scheduled. It's not CFD, so it's not, you know, perfect physics, but it's very good for this type of thing where you can construct, you know, a emulation of a vehicle very quickly, and you can, you know, edit the vehicle with the exact motors and propellers and batteries and, you know, masses of objects, all the parts, just like the real vehicle. And you can quickly gain some confidence that the vehicle's got a chance of flying reasonably. You can see that it actually did gain a fair bit of height there, gained about 15 meters in that back transition. And now it's coming down to land. And of course you can, I've got the transmitter here. If I can stretch the cable out far enough so you can see it. So there's the USB based transmitter, so I can fly the vehicle in manual modes as well as in automatic modes. So, and there it is, it's auto disarmed. So there, and we've got lots and lots of different types of vehicles available here. So this is one of my favorites. I quite like developing in real flight, particularly good for some of the more unusual aircraft, like the tilt vectored quad planes and, you know, those types of things. There's other simulators that are better for different tasks. But this particular one, it was very useful, and it meant that I could get make sure that the control of this type of aircraft was reliable before I flew the real one and destroyed a quite expensive aircraft. Any questions about that at all? Nope. Okay. So, well, I could show you the little editor if you like. So if I go into this editor, it's quite nice in the way you can edit the physics of the vehicle. So you notice that I've got the motors tilted at 10 degrees, both tilted towards the center and tilted towards the outside. That's exactly what it does on the real vehicle. They're tilted like that to give better yaw control. And you can pop in and sort of edit all those things. So we can pop in and have a look and change our motors and our tilt, etc. So there's our motors, and I can change, you know, what noise the motors make and the propellers and the number of blades and the all of those sort of things. Then you can change things like the battery, you know, all of the properties of the battery and all those types of things. So it's quite good for quickly creating a vehicle that mimics a real one. Okay, so that's the end of our 2 hours. Oh, when you disconnect from the editor, by the way, it goes crazy. It's you have to actually hit the reset button here like that, because it disconnects from ArduPilot completely when you disconnect from the editor. So it has no controller at all, and it tends to run the motors in strange ways. Right, so are there any final things we want to cover in this seminar? So I'm guessing from the number of people attending, we've got 31 people, which is great. Oh. Really delighted. And thank you so much, Jem, for suggesting this idea. It's a fantastic idea. So I'll put this recording up on the ArduPilot YouTube channel. And I think this could become a regular event. So now for it to be successful, we need people to submit logs. So I think we might maybe schedule another one once we've got another 3 logs submitted, and we might get somebody else to take the lead if they were willing to put their hands up, you know. So, you know, Paul or Leonard or, you know, Peter or Michael. I mean, it'd be great, Michael, if you, I noticed you're on the call, if you could show it with Mission Planner and show how to analyze logs with Mission Planner. And, you know, I could show it, but just I won't do a very good job of it because I rarely use Mission Planner's log analysis tool, but I know that Randy and Leonard find it great. So, you know, showing that would be really good. If somebody else wants to do a session with plot.ardupilot.org and how to get the most out of that, that'd be really good. So volunteers very much welcome. I think it may be monthly or every couple of months, something like that. We have sessions like this would be good. But the key thing is to have those example logs where people are willing to put up their logs for us to all have a look at.
Tridge, just a kind of a question here, and I'll start off by saying I feel like I'm very reliant on you and your knowledge of these parameters and all of the different values that are in the logs to really do this in-depth analysis. I'd like to be able to do some of this myself, and I mean, I feel like I'll maybe refer back to this video to look up some of the specific things that you brought up in these logs. But is there more a condensed area or condensed documentation on some of these parameters, or where can we find the best and latest information on what those individual values that you were plotting, what all of those are, other than you?
Okay, so there is documentation. So Henry's the expert. Are you still on the line, Henry?
And I think just in general, I have seen the documentation, at least I just had it pulled up, of, some of the more basic ones, current, compass, CMD, CAM, A2, there's a log analysis page on the wiki, but there were a lot of things that you brought up that were definitely not on that page.
That's right. There are, I believe all of the log message documentation is up on the wiki, but I don't usually refer to it myself, so I can't immediately point you to the right page. Henry would be the right one, but Henry doesn't seem to be online at the moment. Unless somebody else can immediately show where that is, I tend to look it up in the code. So Josh has just given a link in the chat to the parameters, but that's different from the log message. There's a separate.
So Tridge, I did find the ones for the log messages.
Great. Can you pop that in the chat?
I do see what you're talking about.
There it is, log messages. Great. So Mishi just put it up there. Okay, so that shows it. So in fact, we could have searched in that one for that parameter for the where to find those messages. I tend to go and look in the code to find the message, like I showed you, when I was looking up that vertical Excel one, but that's just sort of a habit. It is actually all on this page. So for those who haven't seen it yet, I'll just share my screen again. And so, so this page here has all of the onboard log messages, and it shows you the description of each of these fields. And there is a lot, right? Our logs are very, very detailed, and it does take a while to learn your way around them. The standard graphs in Nav Explorer can really help because we have a whole bunch of standard graphs on the menus. And most of those standard graphs are also available in plot.ardupilot.org. And I believe that most of them also work in Mission Planner as well as the sort of standard graphs. But we don't always keep the standard graphs up to date. So I have a lot of extra graphs that I have, because you can save a graph. When you create a new graph in Nav Explorer, you can save it. And I've saved hundreds of extra graphs. And periodically I go and move ones that are suitable across to the standard set of graphs you get to Map Explorer, but I don't, move them necessarily all that fast. So some of them are not in the standard graphs, but you can always just graph it by typing it in manually, like I did for those PSC ones in that last log, where I just, one of the key things is use your tab key. So if you type just, when I'm sharing screen here now. So let's go and have a look at seminar and 20, that one, and we have a look at this log. So, and I'll just make this font a bit bigger so it's a little bit easier to see. When I go graph and I hit tab, it shows me all of the available messages. Right? Then if I take one of those graphs, say PIDP, and I put a dot and go tab, then it'll show me all of the possible fields, right, in that message. Now, it doesn't then give you the help to say what those mean. It would be quite nice if we could go help PID like that, which we can't at the moment. That doesn't work. That would be quite nice to show that the help to display, what that field means, and that would basically show you this information. We haven't done that yet for Nav Explorer, but it would be a nice thing for us to add in there. But at the moment, you have to look it up by looking in these messages here.
Don't worry when the exhibition.
Note that that's Copter's log messages.
That's
not
copters.
planes log messages.
That's
So,
right. If you want plane, then you just replace copter with plane here, and you get all of the plane log messages. And there's a lot, mostly they're in common. There's some differences, but they are things like the navigation tuning messages are different and that sort of thing. But so there's all the plane ones there. And similarly, you can put in rover or sub. Yeah.
Notably, the CTON message is significant.
That's right. CTON and QTON is very different from the ones in copter. All right. Okay. Well, if there's no more questions at all, then I think we might close off this call. Thank you all for attending. I hope that was useful. If you've got suggestions for logs to analyze for next time, please pop them into that discussion on discuss.ardupilot.org, where we've got where we do the planning for this session, and then we will then do it, next time, and maybe in a month or so's time, do the next set of logs. So thanks again, Jem, for suggesting this, and I hope you all have a great day and happy flying.
Thank you, Andrew, for taking the lead in educating us. It was highly informative for myself, so I think that we should repeat it. I think it's good to know the people on the group as well.
And if anyone would like changing the format or how we do things, please make suggestions on that discussed topic. I'm very happy to change things about to be as useful as we can be. Good. All right. You all have a great day, and see you next time.
Thanks.
Okay, bye-bye.